Hello and a very warm welcome to this explainer. I'm going to be your friendly professor today, so consider this your front row seat to the most fundamental classroom in the entire universe. We're taking a journey straight into the microscopic world of chemistry, basically building a mental model of the absolute building blocks of, well, everything around us. So whether you're just looking to solidify your chemistry basics or you've always harbored this deep curiosity about how the universe is actually put together, you are in exactly the right place. Grab your virtual notebooks and let's dive right into this.
So I want to kick things off by posing a classic, kind of mind-bending question directly to you. Think about a block of pure gold. If you take that block and you cut it in half, you still have gold, right? Now cut it in half again, and again, and again. Eventually, you're going to hit a wall. You'll reach a point where you simply cannot divide it any further without fundamentally changing what it is. So what is that absolutely microscopic final piece? Well, to answer that, we have to completely shift our mindset from the big, macroscopic world we can actually see down into an invisible, bustling, microscopic world.
But before we shrink down, we need our ground rules. Section 1, Elements and Atoms Defined.
Now, you know people mix these two terms up all the time. An element is a pure substance made of only one type of atom. Honestly, think of elements as the different flavors of the universe: oxygen, carbon, iron, you name it. An atom, on the other hand, is the physical, individual unit of that element. It's literally the smallest possible particle that still behaves like that specific element. So if elements are the ice cream flavors, atoms are the individual, electrically neutral scoops of that flavor.
Right out of the gate, we've got to clear up another really common point of confusion. A true atom is, by definition, electrically neutral. The positive and negative charges perfectly balance each other out. But sometimes atoms gain or lose negative particles, and when they do that, they end up with a net charge. We call that charged version an ion. Understanding that difference is absolutely crucial because it perfectly sets up our investigation into what's actually creating that charge inside the atom in the first place.
All right, let's grab our magnifying glasses. Section 2, Inside the Atom.
100,000. Okay, think about that number for a second. An atom itself is incredibly tiny. We're talking about 0.1 nanometers across. But the nucleus, that dense center tucked inside the atom, it's about 100,000 times smaller than the atom itself. To put that into perspective, imagine a massive football stadium. If the entire atom is the stadium, the nucleus is a single tiny marble sitting right on the 50-yard line. And this highlights a totally mind-bending truth. Almost all of the mass of an atom is packed right into that little marble, which means the atom and literally everything in the universe, including you and me, is mostly just empty space. No way, right?
Since that tiny center holds all the weight, let's meet the characters living there. Section 3, the subatomic particle roster. Consider this your essential chemistry study guide. Notice the first two particles, protons and neutrons. They both live right in that dense nucleus, and they each have a relative mass of 1. Protons bring a positive 1 charge to the table, while neutrons, just like the name sounds, are completely neutral. Now look at the electron. It lives outside the nucleus, basically zipping around in all that empty space we just talked about, organized into energy shells. It carries a negative 1 charge, but its mass? It's roughly 1 over 1836. Honestly, it's so vanishingly small that we basically just consider it 0 when we're calculating the mass of an atom. So, how do we actually use these particles to identify what we're looking at? Well, every atom comes with what is essentially an ID card. The atomic number, which we represent with the letter Z, is simply the number of protons. And that is an absolute unchanging rule. If an atom has exactly 6 protons, it is carbon, period. If it has 8, it's oxygen. Then you have the mass number, represented by A. That's just the total number of heavy things in the nucleus, so protons plus neutrons. Now, I'm guessing a few of you might have the wheels turning in your heads right now, leading to a super logical question. If changing the number of protons actually changes the element itself, what happens if we leave the protons completely alone, but we just tinker with the number of neutrons?
Well, that perfectly transitions us to Section 4, Isotopes, same but different.
This is where the microscopic world gets really fascinating. Atoms of the exact same element can actually have different weights. We call these isotopes. Isotopes are atoms of the exact same element, meaning, yep, they have the exact same number of protons, but they have different numbers of neutrons. And because neutrons have mass, adding them or taking them away changes the total mass number of the atom. This subtle difference in mass means isotopes of the same element will actually have slightly different physical properties, things like their density or how fast they diffuse.
And this is absolutely crucial, so lock this in. Chemical properties are determined by the electrons. Since isotopes have the same number of protons, they naturally have to have the same number of electrons to stay neutral, right? Therefore, they have the exact same electron configuration. So changing the number of neutrons does literally nothing to the chemistry of the atom. They're going to react in the exact same way in any chemical experiment you throw at them.
Let's look at how this plays out in real life. Section 5. Carbon isotopes in action. Let's take these invisible subatomic variations and make them a bit more concrete by looking at the three main siblings of the carbon family. Notice what stays exactly the same across the board. 6 protons. That is the rule that makes them carbon. But look at the neutrons. Carbon-12 has 6 neutrons. 6 plus 6 is 12. Easy math. Carbon-13 has an extra neutron, bumping it up to 7. And carbon-14 has 2 extra neutrons, bringing its total to 8. It's literally just simple addition happening right inside that tiny nucleus.
And this brilliantly illustrates why understanding isotopes actually matters to us in the real world. Carbon-12 is so incredibly stable and abundant that scientists use it as the universal reference standard. It literally defines the atomic mass unit for every single other element. Then there's carbon-13. It's slightly heavier, but it's also stable, and chemists rely on it heavily for a technique called NMR spectroscopy. That helps us map out the crazy complex structures of organic molecules. And finally, carbon-14. Those extra neutrons actually make its nucleus unstable, which means it's radioactive. Because it decays at a known, steady rate over thousands of years, archaeologists use it for radiocarbon dating to figure out the exact age of ancient historical artifacts. 3 variations of the same element, 3 incredibly different, powerful uses.
Which brings us to our final, kind of provocative thought for today's explainer. If isotopes like carbon-12 and carbon-14 share the exact same chemical properties, meaning they behave identically in a beaker or a test tube, how can chemists sitting in a lab actually tell them apart? We can't use chemistry to separate them, so what do we use? Well, the answer involves exploiting that tiny difference in mass using a fascinating tool called mass spectrometry, which literally separates ions based on their mass-to-charge ratio. But to understand exactly how that incredibly clever machine does its magic, you're going to have to join me for our next explainer. Until then, keep asking questions and definitely stay curious. See you next time.